Okay, so in this video, I'm gonna solve problem number 5, I'm sorry. Okay, so it starts by saying that a toy car with a mass of 1.80 kilograms swims down a track with a position that changes as x of t, and we have some variables right here, alpha minus beta t squared plus gamma t to the third, and it gives us the values for each one of these. So the first thing that we can do is start by actually writing everything down. So we know that our precision as a function of time, which is illustrated as x of t, is just going to be alpha, which we know is 2.25 meters. And and we have to use units in this case. Minus, well, we know that beta is, it tells us right here that it's 3.30 meters per second squared times time to the second. And then we have our last portion, which is plus gamma, and we know that gamma is just 1.50. And this has meters per second cubed time to the third. Okay, and it kind of makes sense for us to have these units, because if we were to put seconds, which is the unit for time, the units that we're going to be using for time, it'll be second squared, which would cancel with the second squared, then second to the third, which would cancel with the second to the third, and we would just be left with meters. Okay, so the question is asking, what is the net force at t is equal to 4 seconds? Okay, so in order for us to find the force, we have to use the Newton's second law of motion, which states that the force is equal to the mass, that the net force in an object is equal to the mass of that object times its acceleration, or F equals ma. Okay, so we have the mass of the car, which is just the car going down, and it tells us that the mass, I'm going to put the notes here, the mass is equal to 1.80 kilograms. Okay, so we're just looking for our acceleration. Well, how do we know? How do we find acceleration? It doesn't really tell us here, but it gives us something else. It gives us the position of the car at any time t. Okay, and another concept that we have to understand is that the second derivative of the second time derivative of a function of position, sorry for that, is equal to the acceleration as a function of time. Okay, so we know that we can derive this function right here 2 times, and that we'll have the acceleration. And this comes from the fact that the first derivative of a function in position with respect to time is equal to the velocity, and that the derivative of the velocity as a function of time with respect to time is equal to the acceleration. So if we were to derive this one more time, we would we would have the derivative of this thing, which would give us this thing, which is just the equivalent of this statement right here. Okay, so let's proceed. We know that this is our function right here. So if we derive one time, we know that it's going to be the derivative of whatever it's here, 2.25. And we're going to forget about the units for now, but just remember that this is a has units of meters, and when we divide it, well, just this thing, just a function of position with respect to time. And when we derive it, we go to velocity, which has units of meters per second, or the change in time. Okay, so 3.30 t squared plus 1.50 t to the third. Okay, so we have that our velocity, which is just equivalent of our first derivative of position, is equal to, well, this is just a constant, so the derivative of any constant, or the rate of change in any constant, is just 0. Okay, so now we're going to have negative 3.30 times the 2, which comes down from the exponent, times t, plus we have our gamma right here, which is just a constant, times 3, which comes down from the exponent again, times t squared. Okay, so this would be our velocity, but we're not really interested in the velocity, so we're just going to derive it one more time. That'll be our acceleration. And now t goes away, and we're just left with the coefficients in front, times 2 plus, and then the exponent on t comes down, just as the 3 did on the previous step. We have t, and there we go. This would be our function of acceleration as a function of time. Okay, so we can simplify this. This would be negative 6.60 plus, well, this is 6, and we can actually do the math here, 1.6, and if I'm not mistaken, this is 90. 60, just confirming. 30, 0, 3, 6, 1, 9. Okay, which is just 90. And this is it. This is our acceleration. Okay, so now just recall that we can we can calculate the net force, and let me put it in here. The net force by multiplying the mass of the object times its acceleration. But this doesn't really tell us anything. It just gives us the acceleration at any point t. So we want to know at what time. Okay, so we go back to the problem, and we can say, what is the net force at t is equal to 4? And this is the time at which we would evaluate. So our acceleration at 4.00 seconds. And now we derive it one time, we have here meters per second. If we derive it another time, we'd have meters per second squared. And this is due to the fact that whenever we're dividing, we're actually taking the rate of change of one variable. In this case, it could be well, we went from velocity to acceleration, with the change in velocity over the change in distance. And this d dt just means that we're taking a small portion of that. So the change in velocity would have meters per second as units, and the change in time would be seconds. So this just simplifies to meters per second squared. And it would be the same case going from position to velocity. Okay, so we know that this is meters per second squared. Okay, so our acceleration at 4 would be negative 6.60 plus 9 times 4.00. Okay, and if we evaluate this, this is 6.60 plus 36. And we have 3 significant figures, and we're going to have 3 significant figures on this case. Okay, so when we're adding, we just keep the one that has the less amount of decimal places. So this would be equivalent to saying that 36.0 minus 6.60. Okay, and if we put this in between parentheses, be the same. We'll have units of meters per second squared. Okay, if I'm not mistaken, we can take, this is going to be 40, 35, and so 29.40 or 0.4. And let's see, if we add it again, we added 60, gives us 30, 6, 36. Okay, so we have an acceleration of 29.4 meters per second squared. And this is our acceleration. We're not really done with the problem, but we just find one of the pieces that we need to solve for actual, well, it's asking for the net force, not the acceleration. So gladly, I'm going to turn the page over. We know that the net force is equal to the mass of an object times its acceleration. Okay, and we know that its mass, so I kind of put it right here, it's 1.80 kilograms. So for the car, and I'm going to put it, well, car, is equal to the mass, which is 1.80 kilograms, times its acceleration. And we found that to be 29.4, and this is its acceleration at 4 seconds. So 29.4 meters per second. 29.4 meters per second squared. Okay, and I'm going to do that real quick. I don't really know this off the top of my head. Okay, and so according to the calculator, this is equivalent to 52.92. But let us count the significant figures. We have 3 significant figures here and 3 significant figures here. So we must either round it down or up. And in this case, 2 rounds down. Okay, so we have 52.9, but we have units which are the composure of kilograms times meters per second squared. So kilogram meter second squared, which just translates into 52.9 newtons. Okay, so there's your answer. So how exactly do we check this? And it would be really cool to check the graph first, so I'm gonna bring that to here.